Hello there, and welcome to the Scientist Sleepy. Have you ever wondered what lies beyond the ultimate cosmic darkness, the point of no return? What if there exists a phenomenon in the universe that acts as the perfect, gentle opposite to the insatiable hunger of a black hole? A place where energy and matter are not consumed, but instead gracefully expelled. Tonight, we embark on a quiet, cinematic exploration into the profound mystery of white holes, the theoretical counterparts to black holes, and ponder their potential role in the grand tapestry of cosmic existence. So for tonight, allow yourself to settle in. Find a position that feels most comfortable, a gentle embrace of stillness. And as you do, consider gently pressing that like and subscribe button, not for us, but for your own future self, ensuring this sanctuary of quiet wonder is always within reach. And as we delve into the ethereal nature of white holes, I invite you to share in the comments below. What cosmic mystery sparks your deepest sense of awe? Your thoughts, like stardust, are welcome here. Now, let us drift towards the theoretical shores of these enigmatic cosmic fountains. White holes are theorized cosmic egress points of pure energy, offering a fascinating counterpoint to the gravitational well of black holes. Imagine, if you will, a celestial phenomenon that doesn't consume but rather expels, not with the chaotic fury of a supernova, but with a measured, perhaps even elegant, outpouring of fundamental forces. Unlike black holes, whose event horizons mark an inescapable boundary, the theoretical white hole possesses an event horizon from which matter and energy can only emerge, never enter. This concept arises from the mathematical solutions to Einstein's field equations, the very bedrock of our understanding of gravity and space-time. When we explore the mathematics that describe the extreme conditions of a singularity, the infinitely dense point at the heart of a black hole, we find not just a one-way street into oblivion, but also, in a mirrored mathematical sense, a potential one-way street out. This theoretical egress point is what we conceptualize as a white hole. It is a region of space-time that cannot be entered from the outside, although matter and light can escape from it. Think of it as a cosmic fountain, perpetually gushing forth the building blocks of the universe, a stark contrast to the cosmic drain of a black hole. The very idea challenges our ingrained notions of cosmic processes. We are so accustomed to the universe expanding, to stars forming and collapsing, to energy dissipating, that the concept of a localized source of constant, outward-flowing energy is in itself a profound shift in perspective. This isn't just about a different type of celestial object. It's about a different kind of cosmic process, a fundamental reversal of perceived directionality. The energy emanating from a white hole, if they indeed exist, would be pure, unadulterated force, perhaps the very essence of creation itself. It's a concept that pushes the boundaries of our imagination, inviting us to consider possibilities that lie beyond our immediate observational grasp. The energy involved would be immense, a continuous stream of particles and radiation, a testament to the universe's capacity for both absorption and emission, for both endings and, perhaps, for perpetual beginnings. The energy isn't being generated in the conventional sense of nuclear fusion. Rather, it's theorized to be a pre-existing reservoir, a cosmic spring that has always been, or perhaps was initiated at the very dawn of time. This outflow could manifest in various forms, from high-energy photons to exotic particles, all pouring out into the cosmos, contributing to its ongoing evolution and complexity. The implications of such a phenomenon are vast, touching upon the very nature of reality, the flow of time, and the origin of matter and energy in the universe. It suggests that the universe is not simply a passive recipient of stellar explosions and galactic collisions, but a dynamic interplay of forces, where regions of intense compression are balanced by regions of equally intense expulsion. This duality, this cosmic push and pull, is a fundamental aspect of the universe's grand design, and white holes, in their theoretical form, embody the push side of this equation. They represent a potential source of the very fabric of existence, a place where the universe continuously replenishes itself, a testament to its boundless creativity. The energy is not necessarily newly created, but rather released from a state of extreme compression, a tightly bound potential that is now unfurling. This outward flow is not a violent explosion but a persistent, almost gentle, emergence, a steady stream of cosmic potential becoming manifest reality. The energy signature would be distinct, not the fleeting burst of a supernova, but a continuous, powerful emission that could, in theory, be detected if we knew precisely what to look for. This energetic egress is what defines a white hole, setting it apart as a unique and profound theoretical entity in the vast cosmic tapestry. It is a concept that invites us to ponder the universe not just as a collection of stars and galaxies, but as a dynamic, interconnected system of creation and unmaking, of absorption and emission, of beginnings, and, perhaps, perpetual rebirths. The sheer purity of the energy involved is what makes this concept so compelling, suggesting a direct conduit to the fundamental forces that shape our reality. It's a thought that can expand our perspective, reminding us of the universe's infinite capacity for wonder and the profound mysteries that still lie just beyond our current understanding. A constant reminder that the cosmos is far more intricate and surprising than we can often imagine, a perpetual unveiling of its boundless energetic potential. And so, we can say that white holes are theorized cosmic egress points of pure energy, suggesting a universe that not only consumes, but also continuously and profoundly gives. The theoretical genesis of white holes speaks of a universe unfurling, a cosmic breath exhaled from the very fabric of existence. Imagine, if you will, the initial moments of our universe, a singularity of unimaginable density and heat. While black holes are often conceived as the inevitable endpoint of massive stellar collapse, their theoretical counterparts, white holes, are envisioned as the inverse, points of origin, cosmic fountains from which matter and energy emerge. The concept of a white hole arises from the mathematical solutions to Einstein's field equations of general relativity, specifically the Schwarzschild solution, which describes a non-rotating, uncharged black hole. This elegant mathematical framework, when extended, suggests not just a region of spacetime from which nothing can escape, but also a region from which nothing can enter, and from which matter and energy are perpetually expelled. It's a profound duality, a cosmic yin and yang where the implosion of a black hole is mirrored by the explosion of a white hole. These theoretical entities are not merely abstract mathematical curiosities. They represent a fundamental aspect of how spacetime might behave under extreme conditions, hinting at processes that could have played a crucial role in the very birth of our cosmos. While black holes are characterized by an event horizon that acts as a one-way membrane, trapping everything that crosses it, a white hole's event horizon is a boundary that matter and energy can only traverse outwards. Nothing can cross it from the outside. This means that any object or radiation would be ejected from a white hole, never allowed to fall in. The singularity at the heart of a white hole is not a point of infinite density where matter is crushed out of existence, but rather a point from which matter and energy are continually being born. This is a concept that challenges our everyday intuition about cause and effect, about beginnings and endings. The genesis of a white hole, in theoretical terms, is often linked to the very early universe, a period of rapid expansion and immense energy. Some cosmological models propose that white holes could have been present at the Big Bang itself, acting as the seeds from which galaxies and stars eventually formed. Think of them as cosmic nurseries, spewing forth the raw materials of creation. They are the antithesis of a cosmic drain. They are cosmic sources. The energy and matter that emerge from a white hole are not created out of nothing in the conventional sense, but rather are believed to be a consequence of the extreme conditions of spacetime at the singularity, a place where our current understanding of physics begins to falter. The very act of a white hole expelling matter could be seen as a continuous process of creation, a constant outpouring that fuels the ongoing evolution of the universe. This theoretical genesis is deeply intertwined with the idea of time reversal. If we were to conceptually reverse the process of a black hole forming and eventually evaporating through Hawking radiation, we might arrive at a white hole. It's as if the universe, in its initial moments, underwent a grand unfurling, with white holes as the conduits for this initial burst of cosmic energy and matter. They are not merely hypothetical objects. They are the whispers of creation, the echoes of the Big Bang made manifest in the theoretical landscape of general relativity. The idea that such powerful cosmic engines could exist, spewing forth the very building blocks of reality, offers a profound perspective on the dynamic and generative nature of the universe we inhabit. The theoretical genesis of white holes is a testament to the universe's capacity for both absorption and emission, for endings and beginnings, a constant cosmic dance of creation and transformation that echoes the very essence of existence itself. Singularity's echo, the unseen source of white hole phenomena. Within the theoretical framework that posits the existence of white holes, a profound and somewhat unsettling concept arises: the singularity. Unlike the familiar black hole singularity, which represents an infinite curvature of spacetime where matter is crushed into an infinitely dense point, the singularity at the heart of a white hole is often envisioned as its inverse. It is not a point of ultimate compression, but rather a point from which matter and energy are eternally expelled. Imagine, if you will, a cosmic fountain, its source hidden from view, but its continuous outpouring shaping the surrounding reality. This unseen source, this singularity, is the engine room of the white hole, the point of origin for all that it ejects. It's a place where the very laws of physics as we understand them are stretched and perhaps even rewritten. When we speak of the singularity in the context of a white hole, we are not talking about an endpoint, but a beginning, an eternal genesis. It is a point where the universe's fundamental forces might be operating in a manner that is entirely foreign to our everyday experience. This is not a place of destruction, but of creation, a continuous eruption of existence. The very idea challenges our intuition, which is so deeply conditioned by the gravitational pull of black holes. We tend to associate singularities with an inescapable doom, a cosmic drain. But the white hole singularity flips this script entirely. It is a singularity of abundance, of outward pressure, of an unending outward flow. It's as if the universe itself has a hidden reservoir, a place where creation is perpetually renewed, and this singularity is the valve through which this boundless energy is released. The complexity of this concept lies in its departure from our direct observational capabilities. We can infer the presence of black hole singularities through their gravitational effects on surrounding matter and light, but a white hole singularity, by its very nature, would be a source of outward radiation, making it incredibly difficult to pinpoint its exact location or to study its immediate vicinity directly. Yet, its theoretical existence is crucial to the very definition of a white hole. It is the engine that drives its outward expulsion, the point from which the universe receives a constant influx of matter and energy. This singularity is not a passive void, but an active, dynamic entity, a cosmic crucible of creation. The very notion of a singularity that pushes outward rather than pulls inward is a testament to the mind-bending possibilities within theoretical physics. It suggests that the universe is not merely a place of inevitable decay and collapse, but also a realm of perpetual renewal and expansion, fueled by forces and phenomena we are only beginning to grasp. This unseen source, this singularity, is the fundamental enigma at the core of the white hole, a testament to the universe's capacity for both profound density and boundless effervescence. It is the whisper of creation echoing from a point of ultimate mystery. The singularity's echo is the universe's ongoing breath of creation, a constant whisper of existence from a point unseen. Gravitational repulsion, the anti-force of the cosmos. The universe, in its grand, silent symphony, is a realm of forces that shape and sculpt existence. We are intimately familiar with the pervasive pull of gravity, the gentle, insistent embrace that holds stars in their galaxies and planets in their orbits. It is the architect of cosmic structures, the unseen hand that guides the dance of celestial bodies. Yet the deep, enigmatic nature of white holes suggests a force that stands in stark opposition to this familiar attraction, a cosmic expulsion, a gravitational repulsion that acts as the universe's anti-force. Imagine, if you will, a localized region where the very fabric of spacetime is not being compressed, but rather is being actively pushed outward. This is the essence of gravitational repulsion as theorized in the context of white holes. Unlike black holes, which are defined by an event horizon from which nothing can escape, a white hole is theorized to possess a similar boundary, an event horizon, but one that functions in reverse. Instead of being a point of no return, it is a point of inevitable emergence. Matter, energy, and perhaps even information are not drawn in, but rather are forcefully ejected outward. This outward expulsion is not a passive overflow, but an active, perhaps even violent, repulsion of spacetime itself. The very concept challenges our most fundamental intuitions about gravity. We perceive gravity as an inherently attractive force, a ceaseless drawing together of mass. To conceive of a localized region where gravity actively pushes away, where spacetime itself recoils, is to venture into profoundly counterintuitive territory. This repulsion is not akin to the electromagnetic force pushing like charges apart. It is a manipulation of the gravitational field itself. It suggests that the gravitational field, under specific and extreme conditions, might possess a dual nature, capable of both attraction and repulsion. This repulsive aspect is what gives white holes their unique character. They are not simply passive repositories of spacetime distortions, but active agents of cosmic dissemination. The theoretical framework for such a phenomenon arises from the mathematics of general relativity, particularly when considering the time-reverse solutions of black holes. If a black hole represents a singularity from which nothing can escape, then its temporal inverse, the white hole, represents a singularity to which nothing can fall, and from which everything must emerge. This emergence is driven by this hypothesized gravitational repulsion. It's as if the universe, in its infinite complexity, has provided a cosmic counterpoint to the black hole's insatiable hunger. Where black holes consume, white holes, in theory, create and disseminate. The intensity of this repulsion is thought to be immense, capable of overcoming any infalling matter or energy. It is a force that actively resists collapse, pushing outward against the very tendency of matter to clump together. This is not merely a weaker form of attraction, but a distinct and opposing force. The implications for cosmology are vast. If white holes exist and exhibit this gravitational repulsion, they could play a crucial role in the distribution of matter and energy throughout the universe, acting as sources of cosmic expansion on a localized scale. They could be the engines that seed new structures, the cosmic fountains from which the building blocks of galaxies are dispersed. The very idea of a force that actively pushes space-time apart, rather than pulling it together, is a testament to the boundless ingenuity of the cosmos and the limits of our current understanding. It is a concept that stretches the mind, inviting us to consider gravity not as a monolithic entity, but as a dynamic force with extraordinary, even paradoxical, capabilities. This repulsive nature is the heart of the white hole's mystery, a cosmic expulsion that defies our everyday experience and hints at the profound, hidden workings of the universe. It is a force that, in its theoretical existence, offers a glimpse into a universe not just of attraction, but of a cosmic push and pull, a dynamic equilibrium of opposing forces. This cosmic repulsion, this outward thrust of space-time, reminds us that the universe is a place of profound duality, where attraction and expulsion are interwoven threads in the grand tapestry of existence. Time's arrow reversed, the enigmatic flow within a white hole. Within the theoretical framework of white holes, a truly mind-bending concept emerges: the reversal of time's arrow. Unlike black holes, which relentlessly draw matter and energy inward, succumbing to the inexorable march of entropy and time, white holes are theorized to be regions of space-time from which matter and energy are expelled, a cosmic fountain spewing forth the universe's secrets. This outward expulsion, this act of defiance against the usual gravitational pull, suggests a fundamental difference in how time behaves within their confines. While our everyday experience, and indeed the grand sweep of cosmic evolution, is characterized by an increasing disorder, a movement from order to chaos, a white hole is envisioned as a place where this trend is inverted. Imagine, if you will, a movie played in reverse. Instead of a star collapsing into a black hole, picture a black hole having perhaps evaporated or reached some ultimate state, then spontaneously erupting, spewing forth the very matter and energy that once defined it, but in a new, perhaps more ordered or at least a radically different configuration. This is the essence of time's arrow reversed within a white hole. It is not merely a spatial phenomenon, but a temporal one. The singularity, the point of infinite density at the heart of a black hole, is a destination from which there is no return, a point of ultimate temporal finality. In a white hole, however, the singularity, or whatever theoretical construct replaces it, is a source, a point of origin for outward-flowing temporal currents. This reversal is not to suggest that time itself flows backward in a manner we can readily comprehend, as if causality itself were undone. Rather, it implies that the processes occurring within a white hole are fundamentally antithetical to the entropic increase that defines the forward march of time in our universe. Instead of a gradual decay and dispersal, there is a concentrated outpouring, a creation or recreation of matter and energy. This outward flow is a testament to the potential for temporal dynamics far stranger than our everyday intuition can grasp. The very nature of causality, our understanding of cause and effect, might be profoundly altered within such a phenomenon. A white hole wouldn't absorb the past. It would, in a sense, be a conduit for a future that is already unfolding outward. The event horizon of a black hole is a one-way membrane, a point of no return. For a white hole, the event horizon would be a boundary from which things emerge, a cosmic threshold crossed only in the outward direction. This implies that the universe's narrative, as we understand it, might have chapters we haven't yet conceived, written in a temporal ink that flows in an opposing direction. It challenges our deepest assumptions about the unidirectional nature of existence, suggesting that the universe might be a tapestry woven with threads of both forward and, in these extraordinary places, backward temporal flow, not in a simple reversal, but in a complex interplay of cosmic forces. The very fabric of space-time, warped and twisted by immense gravitational forces, could indeed possess the capacity for such temporal idiosyncrasies. The outward push, the constant expulsion of energy, acts as a powerful counterpoint to the inward pull of black holes, suggesting a dynamic equilibrium, a cosmic dance where time's direction is not a universal constant but a local phenomenon, dictated by the extreme conditions of these theoretical cosmic entities. This reversal of time's arrow within a white hole is a profound philosophical and scientific puzzle, hinting at a universe far richer and more complex than our current understanding allows. A universe where the beginning and the end might not be so clearly delineated, and where the very flow of existence can take unexpected and wondrous turns, offering a glimpse into the universe's potential for profound and unimaginable transformations. A cosmic symphony played in a tempo we are only just beginning to discern. Within the theoretical embrace of a white hole, time's arrow, that relentless arrow of causality and entropy, seems to take a different path, guiding us not towards dissolution, but towards a cosmic genesis. Information's return, escaping the event horizon's grasp. The event horizon of a black hole, that boundary of no return, has long been understood as an ultimate prison for information. Anything that crosses this threshold, be it light, matter, or the subtlest whisper of data, is believed to be irretrievably lost to our universe, swallowed by the singularity at the black hole's heart. This concept, the information paradox, has been a profound puzzle in theoretical physics for decades, a deep contradiction between the principles of general relativity and quantum mechanics. General relativity suggests that information is indeed destroyed, while quantum mechanics, the theory governing the subatomic realm, insists that information can never be truly lost. It can only be transformed. It is this fundamental conflict that fuels the fascination with hypothetical objects like white holes. Unlike black holes, which are cosmic vacuum cleaners, pulling everything in, white holes are theorized to be their exact opposite, cosmic fountains, spewing matter and energy outward. And crucially, in this theoretical reversal, the information that falls into a black hole might, under certain extreme conditions, be expelled back into the universe through a white hole. Imagine a cosmic echo, a reversal of the inexorable inward pull. The The singularity, not as an end, but as a point of profound transformation, where the very fabric of space-time is so distorted that it can, in a sense, rewind. This isn't a simple replay, but a complex reemergence, where the quantum states of the infalling matter are somehow encoded and released. It's a notion that challenges our deepest intuitions about causality and the irreversible march of time. The event horizon in this context becomes less of a one-way door and more of a conceptual gateway, where the very laws of physics might behave in ways we are only beginning to comprehend. The idea that information might escape the clutches of a black hole, not by some loophole, but by the very nature of its opposite, the white hole, is a breathtaking thought. It suggests that the universe may possess a far more robust and resilient memory than we previously imagined, a cosmic resilience that ensures no piece of existence is ever truly erased, but rather finds a new form, a new avenue of expression, perhaps through the radiant outflow of a white hole. This escape, this return, is not a gentle egress, but a powerful expulsion, a testament to the universe's capacity for profound and unexpected transformations. The very concept of lost information begins to dissolve, replaced by the idea of information in transit, undergoing a radical metamorphosis. The information paradox, a cornerstone of black hole physics, finds a potential, albeit theoretical, resolution in the egress of a white hole, where the secrets of the universe are not buried forever, but are instead reborn into the cosmos. This theoretical mechanism offers a tantalizing glimpse into a universe where endings are merely profound beginnings, where what seems to be annihilated is, in fact, merely being transmuted, ready to re-enter the grand cosmic tapestry through a different, radiant aperture. The information, once thought to be irrevocably lost, is instead recycled, recontextualized, and returned to the universe in a new guise, a testament to the fundamental conservation laws that underpin reality, even in its most extreme manifestations. The escape is not a simple undoing, but a complex process of quantum re-encoding and energetic release, a cosmic act of profound renewal. The whisper of data, once drawn into the dark embrace, may find its voice again in the brilliant outpourings of its cosmic twin. The Planck epoch connection, white holes and the universe's birth. Our journey into the enigmatic nature of white holes, those theoretical cosmic egress points, now leads us to a profound connection with the very genesis of our universe, the fleeting, unfathomable Planck epoch. Imagine, if you will, a time so ancient, so dense, and so energetic that our current laws of physics begin to fray at the edges, revealing possibilities that stretch the very fabric of our understanding. This epoch, occurring in the first 10.3 seconds after the Big Bang, is where space-time itself was being woven, where gravity and the other fundamental forces were unified, and where the seeds of all that exists were sown. It is in this primordial crucible that the conceptual framework for white holes finds its most compelling resonance. While black holes are understood as regions of immense gravitational collapse, the theoretical underpinnings of white holes suggest they are the inverse, regions of immense gravitational repulsion, expelling matter and energy. During the Planck epoch, the universe was undergoing an unprecedented expansion, a rapid inflation that stretched the nascent cosmos to unimaginable scales. This inflationary period, driven by an incredibly powerful, unified force, created the conditions for both the potential formation and the subsequent manifestation of structures that behave in ways analogous to white holes. Consider the singularity at the heart of a black hole, a point of infinite density from which nothing can escape. A white hole, in theory, is a singularity from which matter and energy are perpetually ejected, a cosmic fountain. The extreme conditions of the Planck epoch, characterized by immense energy densities and rapidly fluctuating quantum fields, could have provided the very environment where such repulsive singularities could have formed. Some theoretical models propose that the Big Bang itself might have been, in essence, a colossal white hole event, a singular point of ultimate expansion and creation from which our entire observable universe unfurled. This idea suggests that the initial outward burst of energy and matter that constituted the Big Bang was not simply an explosion asterisk into asterisk space, but rather an explosion asterisk of asterisk spacetime itself, a process that shares fundamental characteristics with the theoretical behavior of white holes. The intense gravitational gradients and quantum fluctuations present during this earliest fraction of a second could have established the conditions for a region that, instead of drawing everything inward, forcefully pushed everything outward. This concept bridges the gap between the observed reality of our expanding universe and the theoretical existence of white holes, suggesting that the very act of cosmic birth might have been a manifestation of white hole physics. The universe, in its infancy, was a realm of pure potential, a place where the extreme conditions allowed for phenomena that defy our everyday experience. The Planck epoch, therefore, is not merely a temporal marker. It is a conceptual gateway, a reminder that the universe's origins are intimately tied to forces and processes that are still, even with our most advanced theories, shrouded in profound mystery. The interconnectedness of the Big Bang and the hypothetical white hole is a testament to the universe's capacity for grand, explosive creation, a cosmic genesis that echoes the very essence of a white hole's outward expulsion. It is within this primal, energetic crucible that the idea of a white hole transitions from a theoretical curiosity to a potential architect of existence itself, a cosmic engine of creation that set the stage for everything we observe today. The universe, in its earliest moments, was a symphony of creation, a grand overture played out in the realm of pure energy and nascent spacetime, where the principles of repulsion and expansion, so central to the concept of white holes, were not mere possibilities but the very forces shaping reality. This epoch, therefore, serves as a powerful reminder that the universe's dramatic birth may have involved phenomena that mirror the theoretical behavior of white holes, a cosmic fountain from which all matter and energy emerged. The universe's first moments, a tempest of creation, were perhaps a grand, explosive act of cosmic gestation, a white hole event birthing everything we know from the void. Hawking radiation's counterpart is the birth of matter from nothingness. Imagine, for a moment, the profound elegance of a universe that not only consumes but also creates, a cosmic dance where endings are intrinsically linked to new beginnings. Black holes, those enigmatic celestial bodies, are known to slowly, imperceptibly, lose mass through a phenomenon called Hawking radiation. This theoretical process, proposed by the brilliant Stephen Hawking, suggests that particle-antiparticle pairs, spontaneously popping into existence near the event horizon, can be separated by the intense gravitational pull. One particle, often the antiparticle, falls into the black hole, effectively taking mass with it, while the other, the particle, escapes into space as radiation. This is a slow, gradual process, a gentle exhalation from the cosmic void. But what if this isn't the entire story? What if there exists a phenomenon that operates in the inverse, a cosmic exhalation that doesn't merely radiate energy, but actively gives birth to matter? This is where the concept of white holes enters our contemplation, offering a theoretical counterpoint to the black hole's insatiable appetite. While Hawking radiation describes a gradual dissipation, a slow fading of a black hole's existence, the theoretical white hole embodies an opposite principle, a continuous, explosive outpouring of matter and energy. It is the universe's grand gesture of creation, a point from which new physical entities emerge, unfurling into the cosmos. This is not merely a theoretical abstraction. It is a deeply philosophical notion that resonates with our innate human desire for renewal and continuity. The idea that from the very fabric of space-time, from a point of unimaginable density and pressure, new forms of existence can spontaneously arise is both awe-inspiring and deeply comforting. It suggests a universe that is not static or finite in its creative capacity, but one that is perpetually in a state of becoming, of unfolding, of giving birth. The implications are vast, touching upon the very origins of matter and the fundamental forces that govern our reality. If white holes are indeed a reality, they represent a cosmic engine of creation, a source from which the building blocks of galaxies, stars, and perhaps even life itself could have originated. This is a stark contrast to the black hole, which represents a point of ultimate density and an end to observable existence. The white hole, in its theoretical manifestation, is the antithesis, a point of pure potential, a fountain from which the universe perpetually replenishes itself. It is a reminder that even in the face of immense gravitational forces and the apparent inevitability of collapse, the universe possesses an inherent drive towards creation and expansion. The very concept challenges our ingrained notions of beginnings and endings, suggesting a cyclical or even continuous process of cosmic genesis. This is not a simple one-way street of decay. It is a testament to the universe's boundless, creative power. The birth of matter from what appears to be nothingness, or from a singularity that defies our current understanding, is a profound testament to the universe's capacity for surprise and wonder. It is the ultimate expression of cosmic generosity, a continuous offering to the vast expanse of space. The theoretical framework of white holes, as the inverse of black holes and the conceptual counterpart to Hawking radiation, paints a picture of a universe that is not only governed by the laws of physics, but is also a canvas for continuous, spontaneous creation. This is the universe breathing out, not in, a profound and elegant counterpoint to the slow, inexorable pull of gravity. And so, the universe whispers its secrets, revealing that even in the most extreme conditions, creation finds a way to bloom. Black hole evaporation and white hole emergence are intricately linked in the grand cosmic dance, suggesting a profound balance in the universe's energetic flows. Imagine, if you will, the universe as an immensely complex, self-regulating system, a vast and ancient organism where energy is constantly transformed, never truly lost, but merely shifts its form and location. For eons, our understanding of cosmic objects was dominated by the seemingly inexorable pull of black holes, entities that consume and retain, their event horizons a one-way membrane into oblivion. Yet the revolutionary insights of Stephen Hawking unveiled a startling counterpoint. Black holes are not eternal prisons. Through the phenomenon now known as Hawking radiation, these cosmic behemoths slowly, infinitesimally, release energy back into the universe. This process is incredibly slow, taking vastly longer than the current age of the universe for even the smallest black holes to fully dissipate. However, the principle is undeniably profound. As a black hole radiates, it loses mass and energy, shrinking over immense timescales. This gradual diminishment, this slow exhalation of energy, is not merely a passive fading. Theoretical frameworks, particularly those exploring the intersection of quantum mechanics and general relativity, propose that this very process of evaporation could be the genesis of white holes. Think of it as a cosmic recoil, a fundamental law of physics dictating that for every absorption there must eventually be an emission, a release, a rebirth. While black holes represent the ultimate absorption, the ultimate gravitational well from which nothing escapes, white holes are theorized to be their exact opposite, regions of spacetime from which matter and energy are expelled, but into which nothing can enter. They are, in essence, the universe's way of exhaling, of replenishing, of creating. The evaporation of a black hole, therefore, is not an end, but a transformation. The energy and information that are seemingly lost within a black hole's singularity are, in this view, not destroyed, but rather reconstituted, perhaps in a new form, at the boundary of a nascent white hole. This creates a remarkable duality, a cosmic equilibrium where destruction and creation are two sides of the same fundamental coin. The immense gravitational forces that define a black hole, pulling everything inward, are mirrored by the hypothetical outward pressure of a white hole, pushing everything away. This balance is not just a theoretical curiosity. It speaks to a deeper, more elegant order in the fabric of reality, suggesting that the universe is not a static stage for celestial events, but a dynamic, ever-evolving entity constantly engaged in cycles of consumption and release, of darkness and light, of absorption and emanation. The very act of a black hole's slow death could be the silent, unseen birth of a white hole, a cosmic balancing act that ensures the continuous flow and transformation of energy throughout the cosmos. The slow fade of a black hole's power is the universe's quiet promise of a new beginning. Wormholes, the hypothetical bridges to white hole realms. These cosmic tunnels, often referred to as Einstein-Rosen bridges, are theoretical shortcuts through space-time, potentially connecting distant regions of the universe or even different universes altogether. While purely theoretical at this stage, the concept of a wormhole is deeply intertwined with the very fabric of space-time as described by Einstein's theory of general relativity. Imagine space-time not as a flat, empty canvas, but as a pliable, three-dimensional sheet. A massive object like a star or a black hole creates a depression or a curve in this sheet. A wormhole, in this analogy, would be like folding the sheet so that two distant points are brought close together, and then creating a tunnel connecting them. This tunnel, the wormhole, would offer a pathway that is significantly shorter than traversing the normal, unwarped expanse of space. The mathematical framework for wormholes arises directly from the equations of general relativity, which describe gravity not as a force, but as a curvature of spacetime caused by mass and energy. Within this framework, it's possible for solutions to exist that describe such tunnels. However, the existence of these solutions does not guarantee their physical reality. For a wormhole to be traversable, meaning for something to actually pass through it, it would need to remain open and stable. This presents a significant challenge, as theoretical models suggest that most wormholes would be incredibly unstable, collapsing almost instantaneously, or would require the presence of exotic matter with negative mass or negative energy density to hold them open. This exotic matter is not something we have observed or can readily create. The concept of exotic matter is crucial here. Normal matter and energy warp spacetime in a way that causes attraction, as we observe with gravity. Exotic matter, on the other hand, would possess properties that warp spacetime in the opposite direction, causing repulsion. It is this repulsive, anti-gravitational effect that could, in theory, counteract the tendency of a wormhole to collapse. Without such exotic matter, any attempt to traverse a wormhole would likely result in being crushed or trapped. The connection to white holes emerges from the theoretical properties of these hypothetical tunnels. If a wormhole connects a black hole to another region of spacetime, it's theorized that the other end of the wormhole might be a white hole. While a black hole is a region of spacetime from which nothing, not even light, can escape, a white hole is its theoretical opposite, a region from which matter and energy are ejected, but nothing can enter. Therefore, a wormhole could potentially act as a conduit, drawing matter and energy into a black hole at one end and expelling it from a white hole at the other. This would imply a cosmic circulation, a grand exchange of matter and energy across vast cosmic distances. The idea of a white hole as the exit point of a wormhole is a fascinating extension of these theoretical constructs. It suggests that the extreme conditions that lead to the formation of a singularity within a black hole might, under certain theoretical interpretations, lead to a point of expulsion into another part of the universe or even another universe. This connection is speculative, of course, but it offers a compelling narrative for how these two enigmatic phenomena might be linked. The very notion of a wormhole challenges our intuitive understanding of distance and travel. It suggests that the universe might be far more interconnected than we currently perceive, with hidden pathways that could, in principle, allow for instantaneous or near-instantaneous travel across immense cosmic gulfs. The theoretical existence of wormholes and their potential link to white holes opens up profound questions about the fundamental nature of reality, the structure of spacetime, and the possibilities for cosmic connectivity. It's a realm where mathematics paints vivid pictures of possibilities that stretch the limits of our imagination, hinting at a universe far stranger and more intricate than our everyday experience might suggest. And so, these theoretical tunnels, these hypothetical bridges through the fabric of existence, hint at a universe where distance is not an insurmountable barrier, and where the cosmic dance of creation and destruction might be far more intimately connected than we ever dared to dream. The thermodynamics of white holes present a fascinating, almost paradoxical inversion of the laws we typically associate with the universe's inexorable march towards disorder. Black holes, as we understand them through the lens of thermodynamics, are characterized by their increasing entropy. Their event horizons act as one-way membranes, swallowing matter and energy, and in doing so, increasing their internal entropy, a fundamental principle that governs the directionality of time and the universe's overall evolution towards a state of maximum disorder, often referred to as heat death. This increase in entropy is intrinsically linked to the loss of information, a concept that has deeply troubled physicists for decades, leading to the famous information paradox. Black holes, in essence, become ever more disordered systems as they grow, their internal states becoming increasingly inaccessible, and their boundaries, the event horizons, becoming smoother and less defined by the specific details of what has fallen in. White holes, however, are theorized to operate in the opposite thermodynamic direction. Instead of absorbing, they are conceptualized as expelling matter and energy. If we were to apply thermodynamic principles to such an object, it would suggest a process of decreasing entropy, or at least a highly unusual form of entropy generation. Imagine a system where order spontaneously arises from what appears to be a more chaotic state, or where information is not lost but actively expelled. This is a profound departure from our everyday experience and our current understanding of the universe. The very concept of entropy, as defined by the second law of thermodynamics, states that the total entropy of an isolated system can only increase over time, or remain constant in ideal cases where the system is in a steady state or undergoing a reversible process. For a white hole to exist and function as theorized, it would imply a localized region where this law is either bypassed, reversed, or interpreted in an entirely new, perhaps more nuanced way. Consider the implications. A white hole could be a source of spontaneous creation, a cosmic fountain from which organized structures and energy emerge. This expulsion of matter and energy would, in a sense, be an act of undisordering the universe, at least locally. While a black hole represents the ultimate sink of information and order, a white hole would be its antithesis, a source of information and potential order. This doesn't necessarily mean that the second law of thermodynamics is violated on a universal scale. Instead, it might suggest that white holes are not isolated systems, and their outward expulsion of energy and matter is balanced by some unseen process elsewhere, perhaps the very formation of the white hole itself from a more entropic state. The theoretical existence of white holes, particularly in the context of extreme cosmic events like the Big Bang, suggests that the universe's journey towards disorder might not be a simple, linear path. There could be cyclical processes, regions of intense creation and organization that temporarily counteract the general trend. The theoretical framework for white holes often arises from the mathematical solutions to Einstein's field equations, particularly those describing black holes. When these equations are run backward in time, or when considering the possibility of matter being ejected from a singularity, the concept of a white hole emerges. These solutions are highly speculative, and their physical realization remains unproven. However, exploring their thermodynamic implications forces us to confront the limits of our current understanding. If a white hole is a region of decreasing entropy, it implies a process that actively generates order. This could manifest as the spontaneous formation of particles, the emission of structured energy fields, or even the outward flow of information that was previously lost within a black hole. The connection to the Big Bang is particularly compelling. Some theories propose that the Big Bang itself could be understood as a form of cosmic white hole, an event from which all matter, energy, and the very fabric of space-time emerged in an ordered, albeit rapidly expanding, state. The initial low entropy of the universe is a cornerstone of modern cosmology, and white holes offer a potential mechanism for understanding how such a highly ordered beginning could arise. It suggests that the universe's history is not just a story of decay and dispersal, but also one of profound creation and potential reorganization. The very act of a white hole expelling matter and energy can be seen as a localized reversal of the entropic arrow of time, a fleeting moment of cosmic order emerging from a more fundamental, perhaps more chaotic, substrate. This unconventional journey of entropy, where it can seemingly decrease in specific, exotic regions of space-time, hints at a universe far more complex and dynamic than our everyday experiences might suggest, a universe where creation and dissolution are in a perpetual, awe-inspiring dance. Within the grand cosmic ballet of creation and dissolution, the thermodynamic journey of a white hole offers a profound whisper of order emerging from the void, a gentle reminder that even in the face of universal dispersal, the seeds of renewal may always be present. Observational challenges: why white holes remain elusive. The very nature of white holes, as theoretical constructs that actively expel matter and energy, places them in a category of cosmic phenomena that are profoundly difficult to detect. Unlike their black hole counterparts, which are characterized by their insatiable gravitational pull, creating a distinct signature of matter falling in asterisk, white holes are defined by their outward expulsion. This fundamental difference in behavior makes direct observation a significant hurdle for astronomers and physicists. Imagine trying to find a source of light that only emits, without any surrounding material to draw attention to itself through accretion disks or gravitational lensing effects caused by mass. The universe, in its vastness, is already a tapestry of faint and distant signals, and a purely emissive object, especially one theorized to be as ephemeral and transient as a white hole, would require an incredibly sensitive and precisely tuned observational strategy. The energy and matter that a white hole ejects are, by definition, moving away from it, making it challenging to pinpoint the origin with the same certainty we can for the event horizon of a black hole, which acts as a point of no return and a discernible boundary. Furthermore, the theoretical models suggest that white holes might be incredibly short-lived phenomena, existing only for a fleeting moment in cosmic time, perhaps during the very early universe, or as the endpoint of a black hole's evaporation. This transience further complicates any attempt at observation. If a white hole exists for only a fraction of a second, or even a few milliseconds, capturing its signature would be akin to trying to photograph a lightning strike from across the globe, a matter of extreme luck and perfect timing. The signals they might produce would also be incredibly diffuse, spreading out across vast cosmic distances, making them difficult to distinguish from the background radiation of the universe. The absence of a strong gravitational pull asterisk inward also means that they wouldn't warp spacetime in a way that is as easily detectable as the extreme curvature around a black hole. While black holes can be identified by the orbits of stars around them, or the intense X-ray emissions from superheated gas spiraling inwards, a white hole would offer no such readily apparent gravitational anchor. The energy it emits would also be expected to be in a form that is already prevalent in the universe, such as photons or neutrinos, making it exceptionally difficult to isolate and identify as originating from a white hole specifically, rather than from more common astrophysical sources like supernovae or active galactic nuclei. The theoretical framework for white holes is strong, rooted in the mathematics of general relativity and the understanding of singularity reversal. But translating these complex equations into observable realities presents a formidable challenge. We are looking for a cosmic echo, a reverse imprint of a black hole's existence, and the universe is a noisy place, filled with countless other phenomena that can mimic or obscure such subtle signals. The very act of asterisk looking for a white hole requires us to anticipate a departure from the familiar gravitational dance of cosmic objects, to search for a place where the rules of inflow are replaced by an outflow of unimaginable power. This requires not only advanced technology, but also a profound shift in our observational paradigms, moving beyond the detection of gravitational collapse to the detection of gravitational expulsion. The data we collect is often a story of what is happening to matter, but with white holes, we are looking for a story of matter emerging a cosmic breath rather than a cosmic gasp. This fundamental difference in the observable interaction is precisely why these theoretical entities remain so elusive, existing more vibrantly in our equations than in our telescopes. The universe, in its silent, vast expanse, offers no easy fingerprints for the ethereal egress of a white hole, leaving us to decipher its potential presence through the faintest of whispers against the grand cosmic symphony. Gravitational lensing, a phenomenon where massive objects bend the path of light, offers a subtle yet profound indicator in our indirect search for white holes. Imagine light not as a straight line, but as a stream that can be nudged and curved by the immense gravitational influence of cosmic bodies. This bending of light, predicted by Einstein's theory of general relativity, acts much like a lens, distorting, magnifying, or even creating multiple images of distant objects. While we typically associate this with the immense gravity of black holes, the very same principles can, in theory, apply to the hypothetical repulsive gravity of a white hole. If a white hole were to exist, its powerful outward push of matter and energy would also warp the fabric of spacetime around it. Light passing near such a region would experience a deflection, albeit in a manner distinct from the inward pull of a black hole. Instead of converging towards a singularity, light might be seen to diverge or to be unusually brightened as it skirts the edge of this energetic expulsion. The key difference, and the challenge for observation, lies in the nature of the deflection. For a black hole, we observe light being bent around it and disappearing, or being stretched and redshifted as it approaches the event horizon. For a white hole, we might theoretically expect to see light being propelled away from a central point with an unusual intensity, or perhaps an anomalous magnification of background objects that appears to emanate from a region devoid of visible matter but rich in outgoing energy. Scientists look for these subtle distortions in the cosmic lightscape. They meticulously map the positions and apparent shapes of distant galaxies and quasars, searching for anomalies that cannot be explained by known gravitational sources like stars, galaxies, or even black holes. A peculiar pattern of multiple images of a single distant source, or an unusual brightening of a specific region of space, especially if accompanied by a distinct energy signature, could be a whisper of a white hole's presence. These lensing effects would not be a direct sighting, but rather a ghostly imprint, a shadow cast by an unseen, yet gravitationally potent, entity. The light itself, traveling across unimaginable gulfs of space and time, carries the story of the forces that shaped its journey, and in those distortions we might find the first hints of these enigmatic cosmic fountains. The very act of light bending, a testament to the universe's interconnectedness, offers us a fragile, yet persistent, clue in our quest to understand the most extreme and elusive phenomena. The curving of light, a silent testament to spacetime's malleability, may one day reveal the outward breath of a universe reborn. The search for exotic matter signatures is a crucial, albeit challenging, endeavor in our quest to understand white holes. These theoretical entities, by their very nature, are predicted to expel matter and energy, a stark contrast to the insatiable hunger of black holes. If white holes exist, They would represent a profound departure from our current understanding of gravitational objects. The challenge lies in discerning the unique fingerprints these expelled substances might leave behind, signatures that would distinguish them from more conventional astrophysical phenomena. Imagine for a moment the very fabric of spacetime. Within a white hole, this fabric is theorized to be in a state of extreme tension, constantly pushing outwards. Unlike the singularity at the heart of a black hole, which draws everything into an infinitely dense point, a white hole's singularity would be a point of infinite repulsion. This outward pressure, this cosmic exhalation, is what we are trying to detect. What form would this expelled matter take? Scientists hypothesize it could be in the form of high-energy particles, perhaps even exotic particles that don't fit neatly into our current standard model of particle physics. These particles might possess unusual mass-to-charge ratios, or exhibit decay patterns unlike anything we've observed before. The energy levels involved would likely be immense, potentially far exceeding those generated by even the most powerful known astrophysical events. Consider the processes that might occur as matter is ejected from a white hole. It wouldn't simply be a gentle stream. It's more likely to be a violent expulsion, a cosmic eruption. This could lead to the creation of unique spectral lines in the light emitted from the vicinity of a suspected white hole. These lines, if detected and analyzed, could reveal the presence of elements or isotopes that are rare or even entirely unknown in our universe. Furthermore, the energy spectrum of this ejected matter might exhibit peculiar peaks and troughs, indicative of the exotic quantum processes occurring within the white hole itself. The very act of creation, of matter spontaneously appearing, would likely imbue it with distinct energetic properties. The search for these signatures extends to looking for unusual gravitational effects. While a white hole would be a source of outward pressure, its immense mass, even if temporary, could still warp spacetime in subtle ways. Detecting these subtle distortions, perhaps through the precise measurement of the trajectories of nearby celestial objects, could offer indirect evidence of a white hole's presence. Gravitational lensing, the bending of light around massive objects, might also behave differently in the vicinity of a white hole, potentially creating unique optical illusions in the cosmos. Another avenue of investigation involves the search for transient phenomena. If white holes are indeed points of energetic expulsion, they might be responsible for sudden, intense bursts of radiation or particle emission that appear and disappear with remarkable speed. These transient events, unlike the more persistent emissions from pulsars or quasars, could be fleeting glimpses of a white hole's activity. The challenge here is to capture these ephemeral events, and then to analyze their properties to confirm they are not simply unusual manifestations of known astrophysical processes. The theoretical framework surrounding white holes suggests they could be intimately linked to the very beginning of the universe, or perhaps to ongoing processes of cosmic creation. If they are indeed responsible for generating matter, then the composition of this matter, its isotopic ratios, and its energy distribution would be a direct window into the fundamental physics of creation itself. This makes the search for exotic matter signatures not just an effort to confirm the existence of white holes, but a profound exploration into the origins of everything we know. The universe, in its infinite complexity, may be whispering its deepest secrets through these elusive cosmic exhalations, waiting for us to learn its language. And in the quiet expanse of the cosmos, the faint whispers of exotic matter are a gentle reminder that the universe is always creating, always offering its wonders to those who listen with patient curiosity. Cosmic microwave background anomalies, whispers of white holes. The faint, ancient light that bathes our universe, the cosmic microwave background, or CMB, is a relic from a time when the cosmos was just a fraction of a second old. It's a remarkably uniform glow, a near-perfect blackbody radiation that tells us the early universe was incredibly smooth and hot. Yet within this near uniformity, scientists have discovered subtle, persistent anomalies, deviations from the expected pattern that have puzzled cosmologists for decades. These anomalies, like unexpected cold spots or regions of unusual polarization, are like faint whispers in the grand cosmic symphony, hinting at something more profound, something that might even connect to the enigmatic nature of white holes. Imagine the CMB as a vast, ancient tapestry, woven with the threads of the very first light. For the most part, the weave is consistent, a testament to the universe's early, uniform state. But here and there, we find a knot, a slightly different colored thread, a pattern that doesn't quite fit the overall design. These are the anomalies. For instance, there's the famous cold spot, a region of the CMB that is statistically improbable to be so much colder than its surroundings. Then there are the alignments of large-scale structures in the CMB that seem to defy our standard cosmological models. Some researchers have proposed that these deviations could be the subtle imprints left by the energetic outpourings of primordial white holes. If white holes, as theoretical constructs, represent points of immense energy ejection, then their activity in the very early universe, during the epoch when the CMB was formed, could have left detectable signatures. These signatures wouldn't be direct observations of white holes themselves, which are incredibly difficult to detect, but rather the lingering effects of their powerful influence on the fabric of spacetime and the distribution of matter and energy at that nascent stage. The idea is that the incredibly energetic events associated with white holes, perhaps the explosive birth of new matter or the violent expulsion of energy, could have created localized disturbances in the primordial plasma. These disturbances, rippling outwards, would have then imprinted themselves onto the CMB radiation as it decoupled from matter and began its long journey across the cosmos. Think of it like dropping a pebble into a perfectly still pond. The ripples, though they fade, carry information about the initial disturbance. In the case of the CMB, these ripples, or anomalies, might be carrying information about events that were far more energetic and fundamental than anything we commonly associate with our current, more settled universe. The challenges in confirming such a link are immense. The CMB is a complex dataset, and distinguishing genuine cosmological signals from instrumental noise or statistical fluctuations is a painstaking process. Furthermore, the theoretical framework for white holes is still under development, making it difficult to predict precisely what kind of signatures they might leave. However, the persistence of these anomalies and the ever-increasing precision of our observational tools keeps the door open to such speculative, yet fascinating, possibilities. The CMB anomalies serve as a constant reminder that our understanding of the early universe and the fundamental forces that shaped it may still be incomplete, and that nature might hold surprises far more profound than we can currently imagine. These subtle variations in the ancient light are not just statistical curiosities. They are potential clues, beckoning us to delve deeper into the most mysterious epochs of cosmic history, and perhaps to glimpse the ghost of a white hole's explosive past. The subtle irregularities in the ancient light of the cosmic microwave background are not mere imperfections, but rather faint echoes of the universe's most energetic beginnings, potentially carrying the signature of a cosmic expulsion, a profound reminder that even in the stillness of the cosmos, powerful forces may have once sculpted existence itself. The role of white holes in galaxy formation theories. The very fabric of the cosmos, in its grandest scales, might owe a debt to these theoretical celestial phenomena. While black holes are famously known for their voracious appetite, consuming matter and light, their hypothetical counterparts, white holes, could be the cosmic architects, the quiet donors of the material that coalesces into the magnificent structures we call galaxies. Imagine, if you will, not a cosmic drain but a cosmic fountain, a point from which energy and perhaps even matter are continually expelled into the universe. This fundamental difference in their behavior from consumption to expulsion positions white holes as a fascinating, albeit speculative, component in our understanding of how galaxies, the vast islands of stars, gas, and dust, came to be. Our current cosmological models, while robust, still grapple with certain early universe puzzles. The sheer uniformity of the cosmic microwave background radiation, for instance, suggests a period of rapid expansion, but the initial seeds of structure, the slight density fluctuations that gravity would later amplify into galaxies, remain an area of intense study. This is where the concept of white holes, particularly primordial white holes theorized to have formed in the chaotic moments after the Big Bang, offers a compelling narrative. These early white holes, born from the extreme conditions of the Planck epoch, could have acted as localized sources of intense energy and particle emission. Unlike black holes, which would have been actively accreting and growing, these primordial white holes would have been continuously spewing forth their contents. This outflow, this gentle, persistent effluence, could have provided the very initial overdensities, the subtle cosmic whispers, that later gravitational collapse would amplify. Picture these white holes as nascent cosmic nurseries, not actively building, but providing the raw materials, the initial energetic nudges that would eventually lead to the formation of larger cosmic structures. As the universe cooled and expanded, the matter and energy expelled from these primordial white holes would have begun to interact. Gravity, the relentless sculptor of the cosmos, would then take over. Regions with slightly higher concentrations of this expelled material, the very regions seeded by the white holes, would have begun to attract more matter. Over eons, these overdense regions would have grown, accreting surrounding gas and dust, eventually collapsing under their own gravity to form the first stars and, subsequently, the first galaxies. The intricate spiral arms, the majestic elliptical shapes, the very arrangement of stars within these galaxies, could, in part, be a legacy of the initial distribution of matter provided by these early cosmic fountains. It's a profound thought that the very foundations of our galactic homes might be rooted in the outward burst of energy from a hypothetical entity that represents the very opposite of the cosmic abyss. Therefore, the theoretical role of white holes in galaxy formation shifts our perspective from mere cosmic consumption to cosmic creation, suggesting that the very structures that house our existence might have been seeded by an act of profound cosmic effluence, a gentle outpouring from the universe's earliest, most energetic moments. Galactic jets are not merely impressive astronomical displays, but potential manifestations of white hole activity, offering a tantalizing glimpse into the energetic outflow of these theoretical cosmic phenomena. These colossal streams of plasma, often extending far beyond the host galaxy, are a testament to the immense forces at play within galactic cores. While traditionally associated with supermassive black holes actively accreting matter, the very nature of a white hole, as a region from which matter and energy are expelled, makes it a compelling candidate for generating such outflows. Imagine a cosmic fountain, not drawing inward like a black hole, but actively pushing outward, a relentless expulsion of exotic particles and energetic radiation. The physics governing these jets is incredibly complex, involving magnetic fields that are twisted and amplified by the intense gravitational and energetic forces. As matter is violently ejected from the vicinity of a potential white hole, it becomes channeled by these magnetic field lines, forming collimated beams that travel at near-light speeds. The energy contained within these jets is staggering, capable of influencing the surrounding interstellar and even intergalactic medium, heating gas, triggering or suppressing star formation, and shaping the evolution of entire galaxies. The composition of these jets is also a subject of intense study, often including relativistic electrons, protons, and potentially other exotic particles that are still poorly understood. The extreme conditions near a white hole, a theorized point of origin for such outward expulsion, would naturally lead to the creation of these high-energy particles and their subsequent acceleration. The process might involve a reversal of the black hole accretion disk phenomenon, where instead of matter spiraling inward and releasing energy, it is violently ejected outward, carrying with it a tremendous amount of kinetic and electromagnetic energy. The sheer scale of these galactic jets, stretching for hundreds of thousands, even millions of light years, suggests an inexhaustible source of energy and matter. This aligns with the theoretical concept of a white hole as a region of continuous expulsion, a cosmic exhaust port from which the universe's rawest energies are released. The intricate interplay of gravity, magnetic fields, and the fundamental properties of matter at these extreme scales is what sculpts these awe-inspiring structures. The very existence of such powerful, directed outflows in the universe begs for an explanation that transcends simple accretion. While black holes are known for their ability to draw in matter, the outward propulsion seen in galactic jets hints at an equally potent, yet opposite, force at work. The concept of a white hole, a theoretical mirror image of a black hole, provides a framework for understanding how such immense outward expulsion could occur. In this scenario, a white hole would act as the engine, continuously feeding matter and energy into the jet, which is then shaped and collimated by powerful magnetic fields. This perspective shifts our understanding of galactic dynamics, suggesting that not all cosmic structures are defined by their gravitational pull, but also by their capacity for immense, directed expulsion. The universe, in its infinite complexity, may be powered not only by its hungry voids, but also by its cosmic fountains, the white holes projecting their energetic essence into the vastness of space. Galactic jets, in their magnificent outward thrust, are like the universe's spoken exclamations, born from an unseen source of pure, unbridled release. Quasars and active galactic nuclei represent some of the most luminous and energetic phenomena in the universe, and their behavior has long been a source of profound scientific inquiry. At their core, these celestial powerhouses are believed to harbor supermassive black holes, actively accreting vast amounts of matter. As gas, dust, and even entire stars spiral inwards towards the black hole's event horizon, they form an accretion disk. This disk becomes incredibly hot due to friction and gravitational forces, radiating immense amounts of energy across the electromagnetic spectrum, from radio waves to gamma rays. This intense radiation is what we observe as a quasar, or an active galactic nucleus, AGN. The process involves matter being compressed and heated to millions of degrees, creating plasma that glows with an intensity that can outshine an entire galaxy. Jets of charged particles are often ejected from the poles of these accreting black holes at near-light speeds, further contributing to the observed energy output and shaping the surrounding interstellar medium. The sheer scale of these events is difficult to comprehend. The energy released by a single quasar over its lifetime can be equivalent to the mass of millions of suns converted entirely into energy. Understanding the precise mechanisms by which matter falls into a black hole, the formation and stability of accretion disks, and the powerful collimation of these relativistic jets remains a significant challenge in astrophysics. While the prevailing model involves supermassive black holes, the extreme nature of these phenomena has led some theorists to explore alternative or complementary explanations, and it is here that the concept of white holes offers a fascinating, albeit speculative, parallel. If black holes represent points of ultimate gravitational collapse, where matter and energy are inexorably drawn in, then white holes, as their theoretical opposite, could represent points of ultimate gravitational expulsion, where matter and energy are forcefully ejected. Could the immense outflow of energy and matter observed in quasars and AGNs, particularly in their powerful jets, be a manifestation of a white hole-like process occurring at the heart of these galaxies? While current models focus on accretion onto black holes, the observed outflows are so energetic and collimated that they invite contemplation of exotic physics. Imagine a scenario where the extreme conditions near a galactic nucleus, perhaps a singularity that has reached a critical point, could reverse its gravitational influence, acting not as a sink, but as a source. In this hypothetical white hole scenario, instead of matter falling in, energy and particles would be continuously and powerfully ejected outwards. The observed jets, extending far beyond the galactic core, could be seen as direct conduits of this expelled energy. The sheer power and luminosity of quasars are so immense that any mechanism capable of sustaining such an output warrants careful consideration. While the evidence overwhelmingly points towards black hole accretion, the theoretical possibility of a white hole's influence, perhaps in conjunction with or as an alternative to black hole activity, offers a compelling avenue for thought. The radiant brilliance and outward-bound fury of quasars and active galactic nuclei, like cosmic beacons announcing unimaginable power, might just be a glimpse into the universe's capacity for both immense consumption and spectacular, explosive rebirth. The multiverse hypothesis and white hole origins. Within the grand tapestry of cosmic inquiry, where the known often dissolves into the speculative, the concept of a multiverse emerges not as a mere flight of fancy, but as a potentially profound consequence of our deepest physical theories. This idea, that our universe might be but one of countless others, each with its own unique set of physical laws and constants, offers a fascinating lens through which to re-examine the very genesis of phenomena like white holes. If black holes represent the ultimate gravitational collapse, the points of no return, then white holes, their theoretical opposites, might be conceived as cosmic egress points, not of matter and energy into a singularity, but from *1, or perhaps from a realm beyond our own observable cosmos. The multiverse hypothesis, in its various forms, provides a fertile conceptual ground for such an origin. For instance, in certain inflationary cosmology models, the rapid expansion of space in the early universe could have created countless bubble universes, each potentially budding off from a parent inflationary field. It is within this framework that a white hole could be theorized as a gateway, a cosmic umbilical cord connecting our universe to another, or perhaps a remnant of the very process that birthed our own universe from a chaotic, primordial state. Imagine, if you will, that the extreme conditions of the universe's birth, a moment of unfathomable energy and density, did not simply result in the singular expansion we observe, but also in the creation of these exotic structures. A white hole, in this context, could be a perpetual fountain of energy and matter, a point of creation drawing from a reservoir of potentiality that exists outside our space-time. This is not a simple ejection of pre-existing material, but rather a process of spontaneous creation, a continuous unfolding of reality from an unknown source. The very act of a white hole expelling matter and energy could be interpreted as a leak from another universe, a cosmic overflow where the fundamental constants of that other realm, though perhaps similar, are not precisely the same as our own. This could explain the seemingly impossible nature of a white hole, its defiance of conventional thermodynamics and causality within our own universe. The energy it expels might not be conserved within our local cosmic budget, but rather be a contribution from an external, vaster system. Such a perspective challenges our ingrained notions of isolation and uniqueness, suggesting that our reality is interwoven with, and perhaps dependent upon, an even grander cosmic architecture. The implications are staggering. If white holes are indeed conduits or remnants of interuniversal processes, then the very fabric of our universe, its origins, its evolution, and its ultimate fate, could be inextricably linked to the existence and dynamics of other universes. The search for evidence of white holes then becomes not just a quest to understand exotic astrophysical objects, but a potential pathway to glimpsing the architecture of a multiverse, a testament to the boundless creativity of the cosmos. The mathematics of quantum mechanics and general relativity, when pushed to their theoretical limits, begin to hint at such possibilities, suggesting that what we perceive as a singular, isolated universe might be an oversimplification of a far more complex and interconnected reality. The very notion of origin for a white hole within our universe could be redefined, shifting from an internal cosmic event to an external cosmic interaction. This challenges our understanding of causality, suggesting that effects might precede their causes, or that causes might originate from realms beyond our direct perception. The sheer energy and matter a white hole is theorized to expel, without any apparent source within our observable universe, lends credence to the idea that its origins lie elsewhere, in a cosmic nursery of infinite potential. This speculative origin from the multiverse, a place where the very rules of physics might be subtly or dramatically different, allows for the seemingly impossible to become plausible, transforming the white hole from a mere theoretical curiosity into a potential key to unlocking the secrets of cosmic genesis and interconnectedness. The sheer scale of such a concept, the idea of our universe being a single note in an infinite symphony of existences, can be both humbling and profoundly awe-inspiring. It suggests that the phenomena we observe, even the most extreme and inexplicable, might simply be the echoes and reverberations of processes occurring on scales far beyond our current comprehension, a constant reminder of the vastness and mystery that lies at the heart of existence. From the boundless cradle of a multiverse, a cosmic breath exhales, seeding our universe with wonders we are only beginning to comprehend, a perpetual echo of creation whispering through the void. Inflationary cosmology proposes a period of extremely rapid expansion in the very early universe, a fraction of a second after the Big Bang. This epoch, driven by a hypothetical energy field called the inflaton field, is thought to have smoothed out initial irregularities, explaining the remarkable homogeneity and flatness of the observable universe. But what if this immense cosmic stretching, this genesis of all that we see, was not merely an outward explosion, but also intimately connected to the very concept of a white hole? Imagine, if you will, that the Big Bang itself was, in essence, a colossal, primordial white hole. Not a singularity that collapsed, but a singularity that exuberantly, explosively emerged. Within the framework of inflationary cosmology, the universe began from a state of immense density and energy, a state from which it ballooned outwards at an incomprehensible speed. This outward expulsion of energy and matter, this violent genesis, bears a striking resemblance to the theoretical behavior of a white hole, a region of space-time from which matter and energy can only escape, never enter. The singularity at the heart of a white hole, a point of infinite density and curvature, is precisely the kind of initial condition that inflationary models require. As the inflaton field drove this exponential expansion, it would have effectively pushed space-time outwards, creating the very fabric of our universe. This process, from a theoretical white hole perspective, would be the ultimate act of creation, a point of no return from which everything we know began its journey. The energy that fueled inflation, the very force that stretched the nascent universe to such vast proportions, could be seen as the outward pressure of this primordial white hole. Unlike a black hole which draws everything in, a white hole acts as a cosmic fountain, a boundless source of outgoing material and energy. If we entertain this profound idea, then the Big Bang was not an event that happened in asterisk space, but rather the creation of space itself, a singular point of egress that birthed our entire cosmic reality. The homogeneity we observe, the fact that the universe looks much the same in every direction, is a natural consequence of such a rapid and uniform outward expansion from a single, fundamental source. The initial quantum fluctuations, amplified by inflation, would have been the seeds of all structure, scattered across this expanding space-time like cosmic pollen. This primordial white hole, therefore, is not just a theoretical curiosity, it is a potential progenitor of everything. It offers a conceptual bridge between the extreme conditions of the universe's birth and the fundamental nature of space-time, suggesting that the very act of cosmic expansion could be a manifestation of a white hole's inherent drive to expel. The universe, in this view, is a grand and ongoing exhalation, a testament to the power of a cosmic beginning that was, perhaps, an ultimate escape. This concept challenges our ingrained notions of beginnings and endings, of inward collapse and outward expansion, suggesting a universe born not from a void, but from a point of infinite possibility and relentless outward momentum. The initial conditions required for inflation, a state of extreme energy density and a mechanism for rapid expansion, are remarkably aligned with the theoretical properties of a white hole. This cosmic fountain, this point of ultimate egress, could be the very engine that set our universe in motion, a singular event of pure, unadulterated creation. The universe, born from an explosive outward surge, whispers of a cosmic fountain, a beginning that was an ultimate escape. Quantum gravity's quest for white hole understanding is a profound journey into the very fabric of reality, a realm where the universe's most fundamental forces collide and intermingle in ways that still elude our complete grasp. Imagine, if you will, the immense challenge of reconciling two titans of modern physics: general relativity, which describes gravity on the grandest scales, and quantum mechanics, which governs the infinitesimally small. These two pillars, while remarkably successful in their respective domains, often speak different languages when we try to apply them to extreme environments, and it is precisely in these extreme environments that white holes reside. They are, in essence, theoretical laboratories for quantum gravity, pushing the boundaries of our knowledge to their very limits. The singularity at the heart of a black hole, or its hypothetical white hole counterpart, is a point of infinite density and curvature, a place where the smooth, continuous spacetime described by general relativity breaks down. Here, quantum effects are expected to become dominant, and a theory of quantum gravity is needed to provide a coherent description. Scientists are exploring various avenues, from string theory, which posits that fundamental particles are not point-like but rather tiny vibrating strings, to loop quantum gravity, which suggests that spacetime itself is quantized, made up of discrete, indivisible units. These theories offer potential frameworks for understanding what happens at the singularity, and by extension, how a white hole might behave. In string theory, for instance, the intense gravitational fields near a singularity might be smoothed out by the extended nature of strings, preventing the formation of an infinitely dense point. Loop quantum gravity, on the other hand, proposes a quantum bounce, where spacetime reaches a minimum size and then expands, potentially resolving the singularity problem and offering a glimpse into the conditions that could give rise to a white hole. The very concept of a white hole, as a region from which matter and energy spew forth, is inherently tied to quantum processes. While black holes are characterized by their event horizon, a boundary from which nothing can escape, white holes are theorized to have a similar boundary, but one that matter and energy can only exit, never enter. This one-way nature, the continuous expulsion of energy, suggests a deep connection to quantum fluctuations and the birth of particles from the vacuum. The extreme conditions required for a white hole to form and persist are so immense that they likely originate from the very earliest moments of the universe, perhaps even from the Big Bang itself. Understanding these primordial conditions requires a quantum description of gravity, as classical physics falters in such energetic and dense environments. The quest for quantum gravity is, therefore, intrinsically linked to the quest to understand white holes. It is a quest to find a unified theory that can explain the universe from the smallest subatomic particles to the largest cosmic structures, and white holes represent a crucial, albeit theoretical, testing ground for these ambitious theories. The challenges are immense. Direct observation of white holes is currently beyond our technological capabilities, and the mathematical complexities of quantum gravity are formidable. Yet, the pursuit of these elusive phenomena drives theoretical physicists to develop new mathematical tools and conceptual frameworks, pushing the frontiers of our understanding of spacetime, energy, and the fundamental laws that govern our existence. It is in this delicate dance between the infinitesimally small and the unimaginably large, between the quantum realm and the cosmic expanse, that the true nature of white holes, and indeed the universe itself, may eventually be revealed. The elegant mathematics and profound philosophical implications of these theoretical constructs offer a tantalizing glimpse into a reality far stranger and more wondrous than we can currently perceive. The intricate tapestry of quantum gravity, in its relentless pursuit of cosmic truths, reveals the potential for white holes not as mere theoretical curiosities, but as profound manifestations of the universe's most fundamental quantum principles, offering a glimpse into the very mechanics of creation and cosmic renewal. String theory offers a profound and intricate perspective on the dynamics of white holes, suggesting that these enigmatic cosmic phenomena might be more than just theoretical curiosities. Within the framework of string theory, the universe is not composed of point-like particles, but of tiny, vibrating strings, each with its own unique vibrational mode. These vibrations dictate the properties of the fundamental particles we observe, from electrons to quarks. When we consider the extreme conditions within a white hole, string theory proposes that the fundamental strings themselves might behave in ways that lead to the outward expulsion of energy and matter, rather than the inward pull characteristic of black holes. Imagine the event horizon of a black hole. According to general relativity, it's a point of no return, a boundary beyond which nothing, not even light, can escape. However, string theory introduces a more nuanced picture. At the Planck scale, the smallest conceivable unit of length, the very fabric of spacetime might be a roiling, energetic sea of these vibrating strings. In the context of a white hole, the singularity at its core, rather than being a point of infinite density that collapses spacetime, could be a region where these strings are vibrating in a manner that actively repels, or unfurls, spacetime outwards. This outward unfurling, driven by the specific vibrational modes of the fundamental strings, would manifest as the expulsion of energy and potentially even matter. Furthermore, string theory provides a potential mechanism for how information, which is seemingly lost in black holes, might be preserved and even re-emitted by white holes. If a white hole is the temporal reversal of a black hole, then just as a black hole absorbs everything, a white hole would be a source of everything. The complex vibrational patterns of strings within the white hole's core could encode the information of what would have fallen into a black hole, and these patterns would then be broadcast outwards as the white hole expels its contents. This offers a tantalizing solution to the black hole information paradox, suggesting that information is not destroyed, but rather transformed and re-emerged through these cosmic fountains. The immense energies involved in the formation and activity of white holes, as theorized by string theory, align with the idea that they could be the endpoints of processes that began at the very dawn of the universe, or perhaps even in other universes. The quantum fluctuations and the specific configurations of string vibrations at these incredibly high energy densities could be the driving force behind such explosive outward phenomena. It suggests that the universe's fundamental constituents, these vibrating strings, possess an inherent capacity for both absorption and expulsion, for creation, and what appears to be a cosmic form of rebirth. Thus, string theory paints a picture of white holes not merely as theoretical opposites of black holes, but as active, dynamic entities governed by the fundamental vibratory nature of reality itself. They are cosmic engines of outward flow, potentially reseeding the universe with energy and information, a testament to the intricate and interconnected nature of existence at its most fundamental level. In the grand tapestry of the cosmos, string theory whispers that even in the most extreme phenomena, like white holes, the universe is engaged in a perpetual dance of creation and renewal, an intricate symphony played out by the fundamental vibrations of reality. The information paradox, a deep enigma in our understanding of the universe, proposes a fundamental conflict between the principles of quantum mechanics and general relativity. Quantum mechanics dictates that information, once created, can never be truly destroyed. It might transform, it might become incredibly difficult to access, but its essence, its unique pattern persists. However, general relativity, specifically in its description of black holes, suggests a different fate. When matter falls into a black hole, it crosses an event horizon, a point of no return. From our perspective outside, all the intricate details of that matter, its composition, its history, its very quantum state, seem to vanish beyond the horizon, ultimately being crushed into a singularity. Stephen Hawking's groundbreaking work on black hole radiation further complicated this, suggesting that black holes slowly evaporate over vast timescales, emitting thermal radiation that appears to carry no information about what fell in. This evaporation, if complete, would mean that the information is indeed lost, a direct violation of a cornerstone of quantum physics. This is where the concept of white holes, as theoretical counterparts to black holes, offers a profound and elegant potential solution. While black holes are characterized by an event horizon that only allows matter and energy to enter, a white hole is theorized to have an event horizon that only allows matter and energy to exit asterisk. Imagine a cosmic outflow, a fountain of existence spewing forth from a point in space-time. If white holes exist, and if they are intrinsically linked to the life cycle of black holes, perhaps they act as the universe's ultimate librarians, meticulously preserving the information that seems to be lost within their dark twins. One compelling idea is that the singularity within a black hole does not represent an endpoint of existence, but rather a transition point. Instead of crushing information into oblivion, the extreme conditions at the singularity could, in a sense, bounce or re-emit that information outwards, but not back into the same region of space-time from which it originated. This outward expulsion of information in a new form at a different time, or even in a different region of the cosmos, would mean that information is never truly lost. It is merely transformed and relocated. White holes in this paradigm become the cosmic archives, the repositories where the universe's lost data is meticulously cataloged and eventually returned. They are the universe's way of ensuring that no story, no matter how seemingly insignificant, is ever truly erased. This perspective suggests that the fabric of space-time itself possesses a memory, a capacity for preservation that transcends our current grasp, and that the apparent paradox is not a flaw in the universe's design, but a testament to its profound and enduring order. White holes as seeds for new universes. The concept of a white hole, as a theoretical cosmic entity, extends far beyond mere egress points for matter and energy. It delves into the very fabric of cosmic creation, suggesting a profound role in the genesis of entirely new universes. Imagine, if you will, that the explosive expulsion of energy and matter from a white hole isn't just a localized event, but rather a foundational act of cosmic procreation. within the intensely energetic and exotic conditions that define a white hole's interior, a realm where our current understanding of physics begins to fray. It is theorized that the fundamental constants and laws of physics themselves might be in flux, or perhaps are being actively established. This isn't a simple recycling of existing matter. It's a potential alchemical transformation, a forging of the very elements and forces that would govern a nascent cosmos. When we consider the singularity at the heart of a black hole, it represents a point of infinite density and curvature of space-time, a boundary beyond which all information is lost to our observable universe. A white hole, in its theoretical opposite, could be seen as a singularity that doesn't collapse inward, but rather expands outward, spewing forth the raw ingredients for a new cosmic dawn. This outward explosion is not a gentle unfurling, but a cataclysmic event, potentially creating a localized bubble of space-time that detaches from our own universe, embarking on its own independent existence. The energy released could be so immense, so fundamental, that it possesses the power to spontaneously generate not just particles and radiation, but the very quantum fields that underpin reality. Think of it as a cosmic womb, a crucible where the fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, are born anew, perhaps with subtle variations that would lead to entirely different cosmic structures and evolutionary pathways. The conditions within a white hole are so extreme that they could act as a natural laboratory for the creation of the initial conditions required for a universe to form and evolve. It's a cyclical view of existence, where the end of one cosmic epoch, or perhaps a violent event within our own universe, could be the very catalyst for the beginning of another. This perspective allows us to ponder that the vastness of our own universe, with its countless galaxies and stars, might be but one iteration in an ongoing, potentially infinite cosmic process. The very act of a white hole ejecting matter and energy could be interpreted as seeding a new region of spacetime with the potential for existence. These ejected particles and fields, under the right, albeit incredibly rare, circumstances, could coalesce, attract, and expand, forming the initial structures of a new universe. This is not merely a theoretical extrapolation. It's a deeply philosophical contemplation of cosmic origins and destinies. If white holes are indeed these cosmic nurseries, then the universe we inhabit, and indeed all universes that might exist, are born from these incredibly energetic, enigmatic phenomena. It suggests a universe that is not static, but dynamic and generative, perpetually in a state of becoming. Our understanding of the universe is often framed by expansion and entropy, by a gradual winding down. But the theoretical existence of white holes offers a counterpoint, a vision of cosmic renewal, a testament to the universe's inherent capacity for creation. It's a profound thought that the explosive heart of a white hole might be the quiet, unseen beginning of countless other realities, a continuous cycle of cosmic birth and rebirth that stretches beyond our comprehension, reminding us that even in the most extreme phenomena, there lies the potential for new beginnings, a gentle promise whispered across the vastness of space-time. The energetic outbursts, a glimpse into white hole power. Imagine, for a moment, a cosmic phenomenon so profoundly energetic, so utterly unlike anything we typically observe, that it challenges our very understanding of how the universe expels matter and energy. This is the realm of white holes, and their defining characteristic, the energetic outburst, offers a tantalizing glimpse into their immense power. Unlike the insatiable hunger of a black hole, which draws everything into its gravitational maw, a white hole is theorized to be a source, a cosmic fountain from which energy and matter are violently expelled. This expulsion isn't a gentle flow, it's a cataclysmic event, a sudden and immense release of energy that could dwarf even the most powerful supernovae we've witnessed. The very concept of a white hole arises from the mathematical solutions to Einstein's field equations, the same equations that so elegantly describe the gravitational pull of black holes. When these equations are explored in their entirety, they suggest not just regions where gravity is so strong that nothing can escape, but also regions where matter and energy are, by their very nature, forced outwards. These are the white holes. The energetic outbursts are not merely a consequence of their existence. They are, in many theoretical models, their primary mode of interaction with the wider universe. Think of it as the universe's ultimate pressure valve, a place where immense internal forces build up until they can no longer be contained, erupting outwards in a spectacular display of cosmic power. The energy released from such an event could be staggering, capable of influencing the surrounding space-time on vast scales. It's a process that, if it occurs, would be fundamentally different from the gradual accretion disks around black holes or the explosive, but finite nature of stellar explosions. Instead, it suggests a continuous or episodic, yet immensely powerful, ejection of the universe's fundamental constituents. The theoretical framework suggests that the energy density within a white hole could be so immense that it overcomes any gravitational pull, forcing a rapid and forceful outward expansion. This isn't just about pushing matter out. It's about the very fabric of space-time itself being stretched and energized by this outward surge. The implications for astrophysics are profound. If white holes exist and are capable of such energetic outbursts, they could be responsible for phenomena we currently struggle to explain. Perhaps some of the most powerful gamma-ray bursts, those fleeting but incredibly intense flashes of energy, are not simply the death throes of stars, but the signature of a white hole unleashing its pent-up power. Or perhaps the mysterious jets of plasma that are seen erupting from the centers of galaxies, often associated with supermassive black holes, are in fact powered by the white hole component of these enigmatic objects. The sheer force involved in such an outburst would be difficult to comprehend. It would be a moment when the universe itself seems to roar, a demonstration of forces that dwarf our everyday experience and even our current understanding of stellar physics. The energy involved could be so great that it would not only push matter outward, but could also warp space-time significantly, creating temporary distortions and gravitational waves that ripple across the cosmos. This energetic expulsion is not just an event. It's a statement of existence, a declaration of power from a region of space-time that defies our conventional notions of gravity and matter. It is a theoretical testament to the universe's capacity for both consumption and creation, for both darkness and blinding light. The immense energy released from a white hole is a reminder that the cosmos is far more dynamic and wondrous than we can currently perceive, a place where forces unseen and energies unimaginable are constantly at play, shaping the very structure of reality with their silent, yet potent, influence. The very nature of these energetic outbursts is a puzzle that continues to captivate theoretical physicists, pushing the boundaries of our knowledge and inspiring new avenues of research into the most extreme environments in the universe. It's a concept that fuels our imagination and reminds us of the vastness of the unknown that still lies waiting to be understood. The energetic power contained within a theoretical white hole is a testament to the universe's capacity for explosive creation, a force that can reshape the cosmos with a single, magnificent exhalation. These energetic outbursts, theorized to emanate from white holes, are not merely powerful events. They are cosmic pronouncements of an outward force that can sculpt the universe, reminding us that even in the most extreme theoretical constructs, there is a profound and awe-inspiring dance of creation and expulsion, a constant ebb and flow that underpins existence itself. Antimatter's potential source lies in the enigmatic ejection from white holes. The universe, in its grand and intricate dance, presents us with profound mysteries that challenge our very perception of reality. Among these, the nature and origin of antimatter stand as a particularly compelling enigma. We know that for every particle of matter, there exists an antiparticle identical in mass but opposite in charge and other quantum properties. When a particle and its antiparticle meet, they annihilate each other, releasing pure energy. The universe, however, is overwhelmingly composed of matter, with only trace amounts of antimatter observed. This stark imbalance, known as the baryon asymmetry problem, suggests a fundamental process in the early universe that favored the creation of matter over antimatter, or perhaps a mechanism for their separation. While several theories attempt to explain this cosmic disparity, the theoretical framework of white holes offers a fascinating, albeit speculative, avenue for understanding where antimatter might originate and how it could have been sequestered or ejected. White holes, as the hypothetical counterparts to black holes, are theorized to be regions of spacetime from which matter and energy can only emerge, never enter. Imagine them as cosmic fountains, spewing forth their contents into the universe. If black holes are the ultimate cosmic sinks, absorbing everything, white holes are their theoretical antithesis, acting as cosmic sources. The very act of a white hole ejecting matter and energy implies a process of creation, or perhaps a transformation of something fundamental. In the context of antimatter, one compelling idea is that the extreme conditions within or at the boundary of a white hole could facilitate the production of antiparticles. Consider the process of pair production, where energy can spontaneously transform into a particle-antiparticle pair, such as an electron and a positron. While this occurs readily in high-energy environments, the question remains, where does the antimatter component go? If a white hole is a source of incredibly energetic outflows, it is conceivable that these outflows could be rich in antiparticles. The very nature of a white hole, being a point of singularity from which things emerge, could be a crucible for generating these opposite counterparts to ordinary matter. The process might involve a reversal of the physics that governs black hole behavior, where a black hole might swallow matter and potentially, through Hawking radiation, emit particles. A white hole could be envisioned as actively birthing particles and antiparticles. The enigma of white hole ejection lies in the fact that we have no direct observational evidence of such objects. Their existence is inferred from the mathematical solutions to Einstein's field equations, particularly when considering the time-reverse scenario of a black hole. If a black hole is characterized by an event horizon that marks a point of no return, a white hole would have an event horizon that marks a point of no entry. Anything attempting to cross it from the outside would be repelled. This suggests an outward flow of information and matter. The energy required to create particle-antiparticle pairs is immense. White holes, by their very theoretical nature, are associated with immense energies and gravitational forces. It is within such extreme environments that the fundamental laws of physics might allow for the spontaneous generation of antimatter. Perhaps the singularity at the heart of a white hole, or the region just beyond its event horizon, is a place where energy is so concentrated and the fabric of spacetime so distorted that it actively produces these antiparticles. Furthermore, the concept of white holes as potential sources of antimatter could help address the baryon asymmetry problem. If, in the very early universe, a process involving white holes preferentially ejected matter while retaining or somehow transforming antimatter, or vice versa, this could have led to the surplus of matter we observe today. Alternatively, if white holes are indeed expelling antimatter, and we simply haven't identified the source, it suggests that our current methods of detection or our understanding of where to look for antimatter are incomplete. The ejection from a white hole wouldn't necessarily be a gentle release. It could be a violent, energetic expulsion, a cosmic burst of antiparticles hurled into the nascent universe. This process could have played a crucial role in seeding the cosmos with the fundamental building blocks of reality, including its less abundant counterpart. The very idea that these enigmatic cosmic fountains could be the source of antimatter, the mirror image of everything we see, adds another layer of profound wonder to their theoretical existence. The ejection from a white hole, a theoretical cosmic fountain, may hold the key to the universe's matter-antimatter imbalance, hinting at a creation process where opposites are born from unimaginable energy. The philosophical implications of cosmic rebirth are as vast and profound as the universe itself. When we contemplate the theoretical existence of white holes, we are not merely engaging in abstract physics. We are peering into the very essence of existence, questioning the linearity of time, the nature of creation, and the ultimate fate and potential renewal of all that is. Imagine for a moment that the universe, in its grand, cyclical dance, might possess mechanisms for not just dissolution, but for a profound and energetic reemergence. White holes, as theoretical egress points of matter and energy, offer a tantalizing glimpse into such a possibility. They challenge our deeply ingrained perception of a universe that progresses inexorably from a singular beginning towards an eventual end. Instead, they suggest a possibility of perpetual renewal, a cosmic alchemical process where the remnants of one epoch, perhaps even the compressed energy of a collapsed star or a dying galaxy, could be reborn, propelled outward into a new era of existence. This concept resonates with ancient philosophical and spiritual traditions that speak of cycles of creation and destruction, of death and rebirth. The idea that something could emerge from a point of intense gravitational repulsion, a mirror image of the black hole's insatiable pull, evokes a sense of awe and wonder about the universe's inherent capacity for transformation. It shifts our perspective from a finite journey to an infinite, unfolding narrative. If white holes are indeed cosmic fountains of creation, then the universe is not a one-time event, but a continuous, evolving symphony of becoming. This contemplation can be deeply comforting, offering a perspective that transcends personal mortality. Our individual existence, though finite, is part of a much larger, potentially eternal process of cosmic generation. The very fabric of spacetime in this view is not a stage upon which events simply occur and then fade, but an active participant in an ongoing act of creation. It suggests a universe that is not just governed by laws of physics, but imbued with a creative impulse, a drive towards new forms, new possibilities, and new beginnings. The sheer scale of this potential rebirth is almost incomprehensible, dwarfing our human conceptions of time and space. Yet, it is precisely this scale, this majestic scope, that can help us find perspective on our own lives. The anxieties and stresses of our daily existence can feel immense, but when viewed against the backdrop of a universe that might be perpetually creating and recreating itself, these concerns can begin to soften. The philosophical implication is one of hope, of resilience, and of an underlying order that is not simply about decay, but about the potential for an eternal return, a magnificent unfolding of cosmic potential. It invites us to consider that perhaps, even from the deepest voids, new light and new existence can emerge, offering a profound sense of peace and continuity. And so, the contemplation of white holes invites us to embrace the universe not as a static entity, but as a dynamic, ever-renewing phenomenon, suggesting that even in the face of cosmic endings, there lies the promise of magnificent beginnings, a testament to the enduring cycle of creation. White holes, a test for our understanding of fundamental physics. The very concept of a white hole, this theoretical cosmic phenomenon that acts as the inverse of a black hole, presents a profound, and at times, unsettling challenge to our current understanding of fundamental physics. It's a notion that pushes the boundaries of our established frameworks, forcing us to re-examine the very laws that govern the universe as we perceive them. Black holes, with their insatiable gravitational pull and event horizons from which nothing can escape, are already mind-bending enough. But white holes introduce an entirely new layer of complexity by suggesting a region of spacetime from which matter and energy can only emerge, never enter. This fundamental asymmetry, this reversal of the unidirectional flow of causality we so readily accept, is where the real test lies. Our current theories, particularly general relativity, describe spacetime as a dynamic entity, warped and shaped by mass and energy. Black holes are a direct and well-supported prediction of this theory, arising from the extreme curvature of spacetime under immense gravitational pressure. White holes, however, are also solutions to Einstein's field equations, albeit under conditions that are far more speculative and perhaps even physically impossible to achieve in our observable universe. The equations allow for them, but the physical mechanisms for their formation and existence remain deeply enigmatic. This is a crucial point. The mathematics permits, but the physical reality is elusive. This disconnect is a fertile ground for scientific inquiry, but also a source of deep theoretical unease. One of the primary challenges white holes pose is to our understanding of causality and the arrow of time. In our everyday experience, and indeed in most cosmological models, time flows in one direction. Events happen, and their consequences follow. Information travels forward. Black holes, in a sense, represent a point where this forward march of information can be seen to terminate for an external observer. White holes, conversely, suggest a point of origin, a source from which events and information emerge asterisk. If a white hole were to exist, it would imply a mechanism that actively pushes outward, that spews forth particles and radiation, seemingly without an external input. This is not merely a matter of reversing a process. It's about understanding the fundamental forces and interactions that could drive such an expulsion on a cosmic scale. Furthermore, the concept of an event horizon for a white hole is fundamentally different from that of a black hole. For a black hole, the event horizon is a point of no return. For a white hole, it would be a boundary that can never be crossed from the outside. Anything approaching it would be repelled. This implies a form of negative pressure or a repulsive gravitational force, concepts that are not readily accommodated by our standard models of gravity. While we have concepts like dark energy that exhibit a form of cosmic repulsion on large scales, the localized and intense repulsive force implied by a white hole's event horizon is something else entirely. It suggests a physics that operates beyond the reach of our current experimental verification and even our theoretical comprehension. The very existence of white holes hinges on extreme conditions, perhaps remnants from the very early universe, or perhaps born from the evaporation of black holes in a highly speculative scenario. If a black hole were to completely evaporate via Hawking radiation, some theories suggest that the final moments could involve the formation of a white hole, releasing the matter and information it has consumed back into the universe. This is a tantalizing idea, offering a potential mechanism for resolving the infamous black hole information paradox. The paradox being that if information is truly lost within a black hole, it violates a fundamental principle of quantum mechanics. A white hole offering a return ticket for this information would be a monumental theoretical victory. However, the observational evidence for white holes is, thus far, non-existent. We can observe the effects of black holes through their gravitational influence on surrounding matter, the accretion disks they form, and the powerful jets they can emit. White holes, by their very nature, would be harder to detect. They would be sources of outgoing energy, but without a clear point of origin that we can pinpoint with the same certainty as a black hole's singularity. The search for them involves looking for specific patterns of energy emission, unusual gravitational lensing effects, or spectral signatures that deviate from expected astrophysical phenomena. The absence of such definitive signals is, in itself, a significant piece of data, telling us that if white holes exist, they are either exceedingly rare, fleeting, or operate in ways we haven't yet imagined. The theoretical exploration of white holes forces us to confront the limits of our current scientific understanding. It pushes us to develop new mathematical tools, to formulate new hypotheses, and to refine our comprehension of gravity, quantum mechanics, and thermodynamics. Are they mere mathematical curiosities, elegant solutions to equations that have no physical counterpart? Or are they genuine, albeit hidden, components of the cosmic architecture, waiting for us to discover the keys to their detection and understanding? The very question of their existence serves as a powerful catalyst for scientific progress, urging us to probe deeper into the fundamental fabric of reality. The study of white holes, therefore, is not just an academic exercise in theoretical physics. It is a profound test of our intellectual capabilities, our willingness to embrace the unknown, and our capacity to imagine a universe far stranger and more wondrous than we might initially conceive. It is a reminder that the cosmos holds secrets that can only be unlocked by challenging our most deeply held assumptions, by daring to ask, "What if?" in the face of the seemingly impossible. And in this grand, cosmic dance of creation and potential destruction, the idea of a white hole, a point of pure outward expression, offers a gentle counterpoint to the all-consuming nature of its black hole counterpart, reminding us that even in the most extreme corners of the universe, there might be a constant ebb and flow, a continuous unfolding of the unknown. The future of white hole research promises to be a journey into the very fabric of existence, a quest to unveil the unknown that lies at the heart of our universe's most profound mysteries. Our current understanding of white holes, while rooted in elegant mathematical frameworks, remains largely theoretical, a landscape painted with equations and abstract concepts rather than direct observation. Yet it is precisely this theoretical foundation that fuels the scientific imagination, guiding our inquiries and shaping the next generation of cosmological investigations. The path forward involves a multi-pronged approach, each avenue designed to probe the elusive nature of these fascinating cosmic entities. One of the primary avenues for future research lies in the refinement and expansion of our theoretical models. Physicists are continuously working to develop more sophisticated mathematical descriptions of white holes, seeking to bridge the gap between general relativity and quantum mechanics. This endeavor is crucial because it is at the extreme conditions of a singularity, the theoretical heart of both black and white holes, that these two pillars of modern physics are expected to intersect and perhaps reconcile. New theoretical frameworks, such as advanced theories of quantum gravity, might provide the necessary tools to accurately describe the behavior of matter and energy within a white hole, potentially revealing mechanisms for their formation and their energetic output. These models will not only aim to explain how white holes might exist, but also how they could interact with the surrounding spacetime, offering predictions that can be tested, however indirectly, by future observations. The elegance of these emerging theories often hints at a deeper, more unified understanding of the cosmos, where seemingly disparate phenomena are revealed to be interconnected aspects of a single, grand design. Beyond theoretical advancements, the future of white hole research is inextricably linked to the development of more sensitive and sophisticated observational instruments. While direct detection of a white hole is unlikely due to their inherent nature of expelling matter and energy rather than accreting it, indirect evidence could be sought through a variety of means. Astronomers are constantly pushing the boundaries of what we can observe, developing telescopes that can detect fainter objects, analyze light with greater precision, and probe deeper into the universe's history. Future instruments, perhaps leveraging the power of gravitational wave detectors to an even greater extent, or employing novel techniques for analyzing cosmic rays and high-energy particles, might pick up subtle signatures indicative of white hole activity. These could include unusual patterns in the distribution of matter, unexpected energy emissions in regions where no source is apparent, or anomalies in the cosmic microwave background radiation that defy conventional explanations. The search will be akin to finding a needle in a cosmic haystack, requiring patience, ingenuity, and a keen eye for the extraordinary. Furthermore, the study of extreme astrophysical phenomena will undoubtedly play a pivotal role. Phenomena such as powerful gamma-ray bursts, the energetic outflows from active galactic nuclei, and even certain types of supernovae might, under specific theoretical interpretations, be re-examined for possible connections to white hole physics. While current explanations for these events are well established, the possibility remains that some of their extreme characteristics could be better understood through the lens of white hole dynamics. This would involve reanalyzing existing observational data with new theoretical frameworks in mind, and crucially, guiding the design of future observational campaigns to specifically search for the predicted signatures of white hole interactions. The iterative process of theoretical prediction and observational verification is the engine of scientific progress, and for white holes, this cycle is just beginning to gain momentum. The exploration of white holes also extends into the realm of computational astrophysics. As our theoretical models become more complex, the need for powerful supercomputers to simulate these scenarios will increase. These simulations can help us visualize abstract concepts, test the stability of theoretical white hole configurations, and predict the observable consequences of various formation mechanisms. By modeling the behavior of matter and energy under the extreme conditions that might give rise to a white hole, scientists can gain invaluable insights that are impossible to obtain through direct observation alone. These digital laboratories allow us to conduct experiments that would be impossible in the physical universe, pushing the boundaries of our understanding. Finally, the future of white hole research hinges on interdisciplinary collaboration. The profound implications of white holes touch upon not only astrophysics and theoretical physics, but also cosmology, mathematics, and even philosophy. By fostering dialogue and sharing knowledge across these diverse fields, researchers can approach the problem from multiple angles, potentially uncovering novel solutions and unexpected connections. The quest to understand white holes is, in essence, a quest to understand the fundamental nature of reality, a journey that benefits from the collective wisdom and diverse perspectives of humanity's brightest minds. This grand endeavor, driven by an insatiable curiosity, will continue to push the frontiers of human knowledge, unveiling the unknown and deepening our appreciation for the majestic complexity of the cosmos. And so, the journey to unveil the unknown continues, a testament to our innate drive to explore the deepest mysteries of the universe, reminding us that even in the most enigmatic phenomena, there lies a profound beauty waiting to be understood. White holes, a cosmic promise of renewal and infinite possibility. In the grand tapestry of the cosmos, where the immense and the minuscule intertwine in a dance of perpetual change, the concept of white holes emerges not merely as a theoretical curiosity, but as a profound intimation of universal renewal. These hypothetical celestial bodies, the theoretical antithesis of their more familiar black hole counterparts, represent points of cosmic egress, places from which matter and energy are expelled, rather than consumed. While black holes are characterized by their insatiable gravitational pull, drawing everything, even light, into their enigmatic depths, white holes are envisioned as fountains of existence, spewing forth the very fabric of space-time, perhaps even new universes. The very notion challenges our fundamental understanding of time and causality. If black holes are the ultimate sinks, the end of all that falls within their event horizons, then white holes offer a counterpoint, a potential beginning, a cosmic breath exhaled into the void. They are not merely theoretical constructs. They are philosophical invitations, prompting us to consider the cyclical nature of existence, the possibility of creation emerging from what seems like an absolute end. The theoretical underpinnings of white holes are deeply rooted in the solutions to Einstein's field equations, particularly those describing the spacetime around a singularity. While a black hole singularity represents a point of infinite density and curvature, a region where spacetime tears itself apart, a white hole singularity is its mirror image, a point from which spacetime is born and from which matter and energy are ejected. Unlike black holes, which are formed through the gravitational collapse of massive stars, the formation of white holes remains speculative. Some theories suggest they could be the other side of a black hole, connected through a theoretical wormhole, or perhaps remnants from the very early universe, a time of explosive creation and unimaginable energy. The defining characteristic of a white hole is its event horizon, but in this case, it acts as a boundary that nothing can enter, only exit. Imagine a cosmic fountain, where streams of plasma, radiation, and perhaps even fundamental particles are continuously projected outwards. This outward flow is not a gentle trickle, but a powerful, sustained expulsion, a testament to the immense forces at play. The implications of white holes extend far beyond mere theoretical physics. They touch upon the very essence of our cosmic perspective. If white holes exist, and if they are indeed points of creation, then the universe is not a static entity, but a dynamic, ever-evolving system of birth, death, and rebirth. This concept offers a powerful antidote to the anxieties of impermanence and decay. It suggests that even from the most profound collapses, new beginnings can arise. The universe, in its infinite wisdom, may possess mechanisms for renewal that we are only beginning to glimpse. The immense energy and matter ejected from a white hole could seed new star systems, new galaxies, or even, as some theories propose, entirely new universes, expanding and evolving in their own cosmic journeys. This idea of cosmic seeding, of a universe capable of self-perpetuation through these energetic outpourings, is not just scientifically intriguing, it is deeply comforting. It paints a picture of a cosmos that is fundamentally generative, a place where endings are merely preludes to new beginnings. In the grand cosmic cycle, white holes offer a profound promise of renewal, a whisper of infinite possibility that echoes through the vastness of space-time, reminding us that even in the face of ultimate collapse, existence finds a way to bloom anew. Our calm exploration has covered the theoretical marvel of white holes, enigmatic cosmic phenomena that stand as the conceptual opposite to the all-consuming black hole. We have journeyed through their potential origins in the universe's earliest moments, their unique gravitational characteristics that defy our everyday experience, and the profound implications they hold for the very nature of time and information. We've considered how these theoretical egress points might manifest, from subtle gravitational lensing to the energetic displays of galactic cores, and how they challenge our deepest understandings of physics, from quantum gravity to the thermodynamic arrow of time. Tonight, we have reviewed the principles of cosmic creation and potential renewal, contemplating how these theoretical entities could be not just an endpoint, but a beginning. We've seen how the universe, in its infinite complexity, may hold mechanisms for not only engulfing but also for releasing, for not only ending but for starting anew. This grand perspective, this quiet understanding of forces far beyond our immediate grasp, can offer a gentle reminder of the cyclical nature of existence, of the constant interplay between creation and dissolution that shapes the cosmos. As we contemplate these vast, unseen processes, remember that the universe is a place of continuous wonder, a tapestry woven with threads of both darkness and light, of absorption and expulsion. Your own existence, a part of this grand cosmic dance, is a testament to the extraordinary forces that have brought us here. Let this knowledge settle within you, a gentle weight of profound understanding that can release the anxieties of the day. It is time to rest now. Allow the quiet wonder of the cosmos to lull you into a deep and peaceful sleep, Sleep well. Good night. If you happen to still be awake, you can drift into the next chapter now, continuing your journey through the universe's most captivating mysteries.